And there we are. I believe we're live. Greetings, fellow nerds. Welcome to another episode of Between Two Nerds. I'm Jeff Doyle, and with me is my friend and co host, Jeff Tansura. Hi, Jeff.
Hi, Jeff. Good to see you as always. And great to be back on the show. We had a bit of a pause for a couple of weeks, but we are
Yeah,
back. And our team is nothing less but our ex Abstra team. It's great
that's,
to see Mansour and Ryan. Guys, really missed you.
that's
Yeah, good
right.
seeing
Hey,
you, good
Jeff.
man.
Yeah, it's good
So,
to see you too.
we've got a couple of great guests and a great topic. I think this is going to be a really interesting show. So before we get started there, let's start with Mansour. Mansour, would you introduce yourself to the viewers?
Yes, for sure. Well, first of all, great to be here. I'm Mansour Karam. I was the co-founder and CEO of Apstra. Apstra was acquired by Juniper a bit more than 2 years ago, and since then I've been leading the Apstra effort at Juniper.
And Ryan,
Yeah. Ryan Booth. I've been a network engineer for probably the better part of 20 plus years now. About halfway through that, I shifted over to software development and network automation as my focus. Moved into Apstra about 7, 8 years ago now. And over the past few years, I've just kind of really started digging deeper and deeper into AI, ML, and how we could actually utilize that in the real world within the networking industry. And so that's where a lot of my focus is right now.
and for you viewers, if you have used Abstract Cloud Labs, Ryan and his team are responsible for the magic behind that. So wanted to put that plug in there too, because it seems like
Thanks.
it's hardly ever that we mention Abstra without having to plug Cloud Labs as a way to go in there and kick the tires a bit. But we're not going to talk about Cloud Labs today. We're talking about artificial intelligence and the role that it maybe currently plays and the role that it will definitely play in the future of networking. And Mansour and Ryan are experts in this area, and that's why we've invited them today. So maybe a good place to start is I was making, when we were syncing up before the show started, I was making some jokes about Chat GPT, but that's really not where we're going. But it's in the news so much lately that it's sort of generating a whole new interest in artificial intelligence, and maybe there's some of that interest that can apply to this show too. But just to start, there's all kinds of terminology out there, and one of the things we were all talking about before the show started was, what's the difference between artificial intelligence and machine learning? You hear both of those terms, but is it the same thing? Is machine learning just an element of AI? Mansour, what are your thoughts about that?
Yeah, I mean, this is actually a good question. AI has had a long history, and if you look at the original definition of AI, it's always been about either mimicking or improving on human behavior, right?
Mhm.
And or human intelligence. And so it's kind of a very broad definition. And over the years, there has been many different techniques that were attempted. One of them being machine learning. Starting with just logistic regression, and then with more complex neural networks, all the way to these very sophisticated, deep, neural networks that we have today. But today, especially, to your point, with all the hype, right, around tools such as ChatGPT, which we can't minimize just how maybe impressive or powerful they are. There has been a lot of, I think, people conflate AI and machine learning, so that now when people say AI, I think there is an assumption that we're talking about machine learning. And and for us, we're very, for us, this is a very this is a conversation we almost have every day, because a lot of what we do, especially when you're automating, is like improving on human behavior. It's like if you're like what is automation for a network engineer? It's like instead of doing something manually, now, whatever you did as a human, we want the software to go and do that, and a lot of times what you really want is for them to do it reliably. And so if, or an autopilot on a plane is another example, right? Where, when you have an autopilot on the plane, you want that autopilot to take over, right, from the pilot. And so, that's kind of mimicking or improving on human behavior. Yet these systems don't utilize much machine learning. In fact, and we can get into that. Maybe in some cases, machine learning is exactly the wrong thing or the wrong approach. Yet, no one thinks of intent-based networking as necessarily an AI system today, right? Because of the definition of or the conflation with machine learning, right? So, yeah, go ahead.
Oh, I was just going to say that the autopilot example is one that I use all the time when I do presentations about automation. That comes mainly from, especially early on. Really, when I was talking about intent-based networking before I ever even joined Apstra, I would use the example that they're because you'd have people in the audience say, I'm never going to turn over my network to machine intelligence, because it's just too risky or whatever. And the example I like to use is there's a study of Boeing 777 pilots that says on average, a pilot on an average mission for a Boeing 777 spends about 7 minutes manually flying the airplane. The rest of the time it's automated. And, it doesn't mean that you're going to remove pilots from the cockpit. At least I don't think we will. Maybe we will someday, but we're certainly nowhere near that. But what it does is simply the automation is taking over the mundane pieces of flying the airplane, so that the pilots are better able to focus on the overall mission. And to me, that is just a perfect analogy for how automation affects networks too. Automation, if it's doing all the mundane stuff, that's less of a distraction for network architects, and they can really look at focus on the larger parts of the business requirements for.
Let's extend it to intent-based networking. And actually, I believe we covered some of that in intent-based RFC, but practically, the configuration part is not necessarily the most complex part of intent-based system, right?
Yeah.
Theoretically, you could do it with Ansible, right? The most complicated part is actually consuming business logic and translating it into networking. And this is when machine learning might become really interesting, especially the NLP or really language processing. How do you create an interface that takes, I've got this application that's business critical, and this is kind of high-level characteristics of the application that would be translated into networking concept. This is, I think, when machine learning can really shine, just doing all the complex translation. Mansour, what do you think?
So, maybe we can break this down a bit, right? Like there is this, at the end, I love to think about engineering is about, you need to choose the right tool for the job. And in that context, right, like when you think of an intent-based network system, or any automation system, there is this notion of like, what is it that I'm trying to accomplish? And there, certainly natural language, large language models have, it's pretty impressive, to witness how far they've come along in their ability to extract semantic meaning, right, from the sentences. And so, there, I think, in fact, it's interesting, when we look at our support cases, right, what is the most like generally with AI, you need to see like what are the patterns, right, because it's all about pattern matching, and we can talk about that more. But so when you ask what are the biggest patterns, and the patterns are around documentation. It's about finding information. It's about and it's about extracting this knowledge, right, that is spread out maybe across support use cases, support cases, or documentation, formal documentation, or data sheets. And so having an ability for the user to just ask a question, and then the machine kind of understanding what the question is, and then going and finding the information, and then maybe even presenting it to an end user in a way that is just articulate and grammatically correct. I think there is a lot of power there, right? And I think that the example you gave is similar in terms of like just an understanding of the human. But then,
but looking into development, I think the user interface is much more complicated than what you do below it, right? Because it needs to be intuitive. It needs to prevent you from hanging yourself while allowing you to benefit from newer technologies and really be agile in the way you use networking.
Right. So,
yeah,
but then
they kind of come together too, in the sense that before we can even get these systems to actually do accurate configuration or accurate management of an infrastructure, we got to accurately translate what we're asking it to do, building that intent, or asking the general questions, and we got to have the system respond with accurate results, or at least enough results where we can then kick off a secondary process to validate those results or fine-tune those results. And so I think it does kind of come together. The LLMs, your ChatGPTs and stuff like that, are doing a great job right now of translating language. We just got to get them more accurate and more validated.
Right. So that's exactly right. And then there's the next step, right, which is once you know what you want, right? You mentioned Jeff, and I'm referring Jeff D, around the autopilot and how pilots only manually pilot the plane for 7 minutes. Some would argue that 7 minutes is 7 minutes too long, right?
Yeah.
Because like for something that where you need actual determinism, right? Humans are relatively slow and unreliable, and and they may not be able to grasp all of the information. So you could actually even argue that that's relatively stupid compared to some of these systems that you have on these planes, as long as they take into account all of the parameters and they have all the right rules in them, right?
Yeah.
And so to me, at the end, if you look at that aspect of like translating what the humans want into actual behavior deterministically in the system that you're controlling, I think that software can actually do a phenomenal job. But one can argue, I think that what we've seen, at least, and through my experience, like you do not, you want determinism, right? What you really want is causal systems. You want, if you want to know that if I press this button, these are the things that are going to happen in sequence, and this is the result that I expect. So for us, coming from inventing and having brought intent-based networking to market, right? That has that is kind of the power of it, right? The number one requirement for network operators, which I suspect is the same for pilots, is reliability. Like for networks, we all talk about these 5 nines of uptime.
Mm-hmm.
If you press a button, how do you get the network operator to trust the software? And you get there by ensuring that your software will deliver every time. If you want your network to behave in a certain way, and that's your intent, you want to know that once you press this button, the software will go and deliver it to you every time, deterministically guaranteed, right? And so to me, like when you think of pilots, when you're as a human stepping away and giving the controls to software, there is like the only way to achieve this is through deterministic behavior. You need to have the ability to predict deterministically what this software is going to do, right? And so I think that for us, if you think of it this way, then when you think of deterministic systems versus more like probabilistic systems, machine learning are actually probabilistic systems. And so it kind of it clarifies, in our view, what you can do with deterministic systems versus probabilistic systems like machine learning. And certainly machine learning can't be in the pilot seat, right? Because of that.
I'm sorry, go ahead, Jeff.
I really like to use Maslow's hierarchy of needs for networking analogy, right? Your foundation is really healthy network. If network isn't healthy,
Right.
nothing really matters. You need to feed it. It needs to have basic needs addressed. On top of this, you start building improved performance, improved ability, and we need to clearly differentiate between ability to implement intended state. So network should work. It should pass packets, particular rates, no loops, just basic stuff. And then there's a whole number of layers. How do you make it better? But they all build on top of each other. And some of them could be probabilistic. But the fundamental layer, I mean, if you build a network with loops, it doesn't really matter what you do on top.
Right.
And that's right. Where I can kind of see machine learning and AI, usually you see machine learning as one element of AI, but I can kind of see those as being different things based on what you were saying about probability. And what pops into my head is root cause analysis, where, looking just in the world we live in, or the world you used to live in, Jeff, we're working with a data center fabric, and and doing what we can to automate that. But there's all these systems attached to the edge, routers and firewalls and all of those kind of things. And if there's some anomaly there, it's something that we've been involved in talking about before, but you may not, because our fabric that we control, specifically talking about Apstra in this particular instance, but it could be any intent-based system, doesn't have direct access to that external router or external firewall or something like that. And if something goes wrong, we can still use probability, right, to sort of say, well, there's a 95% probability that someone changed, this particular stanza of a security policy on this firewall, even though you don't have access to say that.
And I think this brings us to discipline in design, right? The degree of probability defines whether it's usable or not. If it's 99%, you actually should use it. If it's 63%, probably you shouldn't. And removing all this weird permutations you see today's networking, from using like MCLock to, better than me, right? To having strictly limited set of permutation network, following same design patterns that are repeatable, that are well understood. And I mean, distributed systems are mathematical, right? You can really understand the behavior and end state if you don't create any deviations out of it. So I think network engineers among us should really think about what they're building and how is it going to behave. Do they fully understand what they're trying to do in terms of distributed systems? And then your probabilistic analysis could go up to 90+%.
Right. So I mean, at least, so the way I've through kind of, so being at Juniper, we also got exposed a lot to AI, as you know, the company acquired Mist many years ago, before AI was as hyped as it is before. And there are certainly lots of use cases there, especially with AP placement, right? For best Wi-Fi signal, where there is a lot of applicability. So we for us, every day we think about, like, okay, these are the use cases we want to deliver to our customers, and what's the best tool available to us to deliver on these use cases. And to me, like, it seems like there are two categories of things, right? Like, roughly, right? One is the environment I have control over, where I know all of the data or the state of this environment. I have knowledge of every aspect of this environment. And certainly, with Apstra, within the context of the network that we control, we can claim that we know, pretty much everything about this network. And if we don't know something, it's just a matter of collecting this telemetry. We should just go and grab the telemetry and build knowledge of it. And it gets really sophisticated. We have a distributed data store that's pops up, but then all of the state is represented in a graph. So we're capturing all these relationships. But once you have that, you don't have to guess, right? When I say you don't have to guess, there is no use to probability. You know everything about the environment, and therefore, if you want something to happen, it's just a matter of making sure it happens. If you want to predict what's going to happen if you do this or that, then mathematically you'll be able to calculate it, and you'll be able to tell deterministically what's going to happen, and that's how you can guarantee reliability. And so, in a sense, if you have all this knowledge, then you should strive to do things deterministically, because then that's how you get to the highest level of reliability, like the autopilot on a plane. The plane is a very defined, constrained environment, right, where the software needs to know every aspect of how this plane behaves and all of the state on this plane. The challenge, though, is that the world is not this perfect or black and white, right? A lot of times, and certainly even with Abstra, there are tons of elements outside of our boundaries, right, outside of our direct control, and some of the problems you're facing could be caused by issues that are happening outside of your domain of authority, and so that's where you don't know everything, and therefore, to your point, Jeff, you need to start thinking of other techniques, right? And we talked about root cause identification, and with Abstra, we've really gone down that path of, trying as much as possible to grab information, it's even outside the domain of authority, in things that are relevant to our environment, so that if there are pieces of data that are relevant as to why a problem is occurring, we should have that piece of data in our distributed data store, so that we can, root cause what's going on. But even then, there are some situations that are going to occur where you don't have that piece of data, and you're going to have to make probabilistic.
The more variability and permutations to introduce, the more. So, but you made really great point, and I think we need to go back and look into cost of lost packet. Taking Jeff's analogy, what happens if autopilot made a mistake? I mean, plane will go down, right? So probably you don't want to make a mistake. If we take classical TCP/IP networking and you lose a packet, most probably it's TCP, most probably TCP is going to retransmit it. So in most cases, if application is not really badly written, it will survive retransmission, right? So the cost of lost packet is negligible. If you lose 1,000 packets, probably it's going to get worse, still probably not deadly.
It depends on the application too, though.
Yeah, but practically it's a survivable event. Now, why are we care so much about network performance these days? Because machine learning mostly, right? In one, nothing really changed. We went from ATM to SDH to Ethernet, from 10 to 50 to 100, now at 800 gig. But networking is still pretty much the same, right? Data center is changing significantly, and now we are going to talk about machine learning using networking, not the other way around. So if you look at average model 5 years ago, it would be run on a single GPU. It had enough CPU cycles, had enough memory to be just contained within single GPU. So you didn't really need networking. 3 years ago, we figure out probably we can still be within a rack. So we can create something that communicates with each other without really hitting IP network or DMA network. Now, if we look at GPT-3, it uses 175 billion parameters. If we look at GPT-4, it could use something between 1 to 50 trillion parameters. If you look at need for memory, for CPU cycle processing, we are not talking about 10 or 100 GPUs. We are talking about 10,000 GPUs talking to each other. And don't forget, GPUs are hot. So how many of those can you have on a rack? Probably 30, 40, definitely not 1,000, right? So you are building data center at scale of 5-stage CLO that do only machine learning. What's also interesting, so Google introduced, let's forget about Google, most of machine learning
the optical
models,
network, right?
yeah, they use collective operations. So different nodes, different locations are interdependent on each other finishing. And if someone is slow, the rest is going to wait for it. If someone has lost a packet, the rest is going to wait for it. So now cost of lost packet is multiplied by size of collective. So it could go in millions of dollars potentially, right? So now this is where performance of the network, reliability of the network takes very different dimension in terms of cost. And this is where we also introduce kind of language between machines and network. Because if you look at traditional TCP IP network, the only thing that host could do is probabilistically guess about latency if you use congestion control that's based on timing, or you could guess congestion if you use something like ECN marking or traditional congestion control techniques. But it's all very probabilistic, and a host can actually make things worse, not better. So a couple of years ago, there's a lot of efforts in industry to provide this kind of set of APIs or language between switches or networking and hosts, so both sides can know exactly what's going on. And this is what introduces this variability and a lot of permutations that are kind of, there are people who are expert in networking domain, there are people who are expert in host domain, but very few people who are in between. And this kind of overlap is not well understood, and this is where the reliability really mandatory. So ability to explain each other, this is how I'm doing, and this is what you could do to make it better. It's so important, and it's because of cost of packet loss. It's because of requirements to run very hot. So again, if you look at traditional data center, most of them are below 50%. So you lose the link, okay, I can steal your route. You lose the switch, okay, I can steal your route. Machine learning networks usually run at 90+%. Otherwise, you just don't get enough bandwidth. The requirements for bandwidth are huge. So
maybe
you need something to adjust network before you actually fail someplace.
So just to kind of, again, break it down a bit, and I know that we have a very technical audience, right? But I think that at the end, I mean, the starting point here is the reason why these are very different type of workloads is because of, this concept of vectorization, right? Maybe you want to, we want to talk about this, right? But essentially, when you're training in AI systems, you're training hundreds of billions of parameters, right? And so in some cases, certainly like with ChatGPT, and when you're doing that, training could take centuries, unless you do it super efficiently. And the way to do it super efficiently is, GPUs. This is where GPUs come in. Is that you have an ability to do operations of massive amounts of data in parallel, right? But then the assumption there is that you have an ability to kind of push all this data at once, through a network and have this computation happen. And then all of the data needs to be shipped somewhere else at once. And if any of the pieces of data is missing, so like if packet drop, forces, one computation not to happen amongst billions, essentially it grinds the whole thing down, right? And you have to go back and do that computation again, or it just slows you down. And so that's kind of like the starting point as to why you now have all of these new requirements on networks. And I think you mentioned one, which is bandwidth. Yeah, I mean, at the end, you're network constrained. And this is why now 800 gig, is kind of like where we're going, and then even beyond that, right? Because like at the end, the network, and you're running these hot, to your point, because the network is the bottleneck. But then I also heard that there were, I mean, to my understanding is that there are also these issues with load balancing, right? ECMP. I mean, so to me, that kind of, the question is, do we need newer topologies, right? Do we need newer protocols, to support all this? Because ECMP, if you have lots and lots of different flows and it's super well balanced, and at the 5-tuple level, I can, load balance across my links, ECMP works fine. But then if I have this types of situation and it's just one, big stream of data going with one 5 tuple, right? Because of one computation, you may have hundreds of links, yet there is only one link that's being utilized, right?
So that's a topic very close to my heart, and I would like to. I spent a couple of years working on this, right?
So tell me, go ahead.
It's a very close to my heart topic. So if we take average ECMP network, and this is what Mansour so rightly mentioned, there's a big difference between throughput and goodput. Your throughput could be 800 gig. Your goodput is probably going to be below 400. And the answer is very simple, ECMP collisions. When we do ECMP, at least in its kind of default behavior, we just distribute traffic per flow across all next hops available within particular ECMP group, independently whether it's elephant flow, mouse flow, independently of its characteristics. And we do it per flow to avoid out of order packets. They're pretty deadly for TCP. They're pretty bad for anything that doesn't use RDMA. RDMA actually allows you to get DMA into memory and then reorder the packets. But we'll touch upon RDMA later on. So practically, if you use your vanilla data centers of today, your GPU or machine learning network is going to suck big time. It's the right term for it. Believe me, it's going to suck.
Right, yes.
So the question here, do you need different topologies? Do you need different tooling? Do you need different protocols? And we kind of independently worked over the years over more complex topologies. So Dragonfly Plus probably would be the next to Claw. We talked about Rift many times on the show. Rift is an amazing protocol to provide much better, much faster routing than anything available today, specifically for this network. Besides some other stuff in Rift, such as KV store, everything you could do with in-band signaling, but that's kind of another very close to my heart topic. Practically, because of tight integration of GPUs to networking, you cannot afford to do only networking. Say, guys, on the host side, it's your problem, like we traditionally do in enterprise, right? You've got networking team, you've got host team. In most cases, they hate each other, but they live together. So practically now you need teams that understand both. And given kind of very scarce amount of people who can do both really well, this is where machine learning could really help to take feeds from both sides and come up with something that's actually relevant and understand. And why is it so important? Any machine learning networking as of today is considered to be lossless. What lossless really means is to think. When you start building queue, you either signal back to sender, please don't send as fast. If it doesn't work, as of last resort, you'll issue an PFC or pause frame and ask downstream not to send traffic to you. Mm-hmm. So the tuning of ECN is a black art, right? There's a number of white papers, mostly by Microsoft, because they use DC-QCN, which is DC version of QCN, practically used everywhere today where you use RDMA over IP UDP, which is RoCE v2. It's complicated. You need to understand very, very well ASIC architecture, cable lengths, and again, it's kind of constant tuning of parameters as you upgrade to new silicon, different optics and whatnot. So making this process automatic where actually host can understand at which speed to send, how to distribute load, potentially hinting the network, look, this is the flow that you can load share per packet. So load sharing per packet removes all the ECMP collisions. This is flow, let's say TCP, for which out of order is out of question. So if you load share, it has to be done per flow. And only host knows what it is. I mean, network has no idea. It only sees an IP packet at the end, right? So if you can start signaling this end-to-end to create a cohesive story between hosts and network, this is where you can get to this much higher loads, virtually lossless network, while still operated by the same people who operated the network yesterday and probably tomorrow.
Yep.
A lot of what you guys are saying is is really around the dynamics or the mechanics of the network itself. But as far as a role for artificial intelligence, do you see that as being more of, with a tip of the hat to Cisco and their terminology, application centric infrastructures, where the network itself is more aware of, and we could bring in intent-based networking there also, that the network is aware of what your intent is for that network, and which really implies being aware of the applications and balancing. Here's all the demands I've got right now in this specific second of the applications I'm supporting, and how do I adjust the network to support those applications? So I'm prioritizing what's the most important, and kind of a QoS, but without the architect having to fool with it, I guess.
The term is great. The implementation is not so, if you talk about it. Right? But besides the point, you're very much right, because as in any other case, your intent is to provide particular characteristics to particular workloads. Question, how do you communicate to your network what's needed? So you need, again, a language between application or networking host on application towards the network. Mm-hmm. You need network to be able to tell the host, slow down, change entropy, do something about it, so I can provide you with SLAs that I offered you before. And it goes back, again, to establish an intent. How do you do this? How do you express your need for particular characteristics? Number two, how do you implement this intent in distributed system? Because now you're not only touching switches, you're touching NICs, you are touching particularly smart NICs, right? So how do you know who gets what information? Now you've got telemetry that's coming not only from the switches, but also from NICs, potentially from GPUs, like NVIDIA is using Nickel, for example, that does this kind of network-wide optimization, right? And it's a really complex scenario with a lot of permutation. So the question whether we as humans can actually build something that's statistically based for this, or we just give up and say, we need machine learning because of amount of variables, because of complexity, and because we just cannot comprehend what we need to be doing.
Yeah, I mean, to me, so there is this. Intent-based networking definitely has a role. I mean, the way to think about this is that we have different use cases, right? A fabric is a fabric, but really there are differences in fabric. Like if it's your typical cloud data center versus like it's an edge data center, we have a collapsed spine design. If you're doing data center interconnect, if it's a campus network, if it's a distributed access, and I think machine learning is, in a type like, okay, if the use case is machine learning, then what is the right fabric for that? And I think that, to me, a lot of the things you said, Jeff, here are pertain to, the requirements or the maybe characteristics, right, of this foundational network, right, that is going to run machine learning workloads efficiently. Right, and I think you touched upon Rocky. You touched upon the limitations of ECMP, the need for bandwidth, and then there is lots of other considerations like, do you need to get this lossless, right? Because we all agree lossless is critical. Is it better to have these super low latency devices, with mechanisms to avoid packet loss versus just deep buffer architectures, right? Versus, even we didn't touch upon it, but then there are some folks deploying InfiniBand. Some of these clusters just have built-in InfiniBand versus Ethernet, which is
most of them, I would say, having some visibility.
Both of them today, right? And so there is that aspect, and then once you define that as a kind of the foundation, right? Then you layer intent-based networking on top of it to ensure, right, that these behaviors match what the user wants, right? So like if we have an intent, then the intent-based networking system, as we described, you can then rely on that system to take over and pilot, the
So
network.
to your
right?
point, InfiniBand as of today is fully intent-driven system. It's the way SDN looked on Nick McCone's slides, right? You've got centralized controller that takes intent northbound, configures the network, configure the switches, configure the quality of service, understand what host is doing, understand what switch is doing. So it's a box that's very predictive in terms of what it does. And it does a lot of Mansour described, right? You put a box, it has interface here, interface there, and it works. That's why people who need high performance today deploy InfiniBand, right?
So I'm just very tempted, because to share this, my experience there I was there in the very early days of Arista, right? That was back in 2005 and 6, 7, and at the time, it was kind of the start of what we call the cloud today, right? With Google, was one of the first that were scaling out these east-west architectures where, when you have a request coming in, now you need to touch many servers and do tons of computations before you can respond. And so these north-south architecture that Cisco was standardized on at the time with the access distribution core just weren't a fit. And at the time, it's funny to think about today, but like we were 1 gig was the norm, and 10 gig was kind of luxury, right? And I think Cisco was selling 10 gig at like something like $5,000 as a port, which meant that like if you're Google and you're trying to build one of those networks, it's completely out of reach, right? And so before Arista came in, right, there was this, InfiniBand, was there, and it was very successful within high performance computing clusters. And it was the technology that came in first in delivering this really cheap, bandwidth, much lower latency than Ethernet. And even the high frequency traders like on Wall Street, starting deploying InfiniBand. And for a while, it felt like InfiniBand was way ahead of Ethernet, right? But then, if you look at it 10 years from then, or like as history progressed, it's, they like to, I think that there is a saying that goes something like, you don't want to sprint in front of a moving train, And so what happened over time is that Ethernet just took over completely, right, into the cloud environments and the banks and high frequency trading, etc. Because there's just so much, energy, momentum, investment, ecosystem, right, in the industry around Ethernet. But when I look at some of these discussions today, it kind of reminds me a bit of those days. In the context of now, instead of cloud, we're talking about AI clusters. And yes, InfiniBand seems to get to it faster. To your point, it's predictable, etc. But then I think that there is a lot of motivation the industry has to kind of catch up and take over with Ethernet. So it'll be interesting to see how things evolve. But as a betting man, I know where my bet will go.
So this is really interesting discussion. And again, it's kind of driven by requirements for scale, right? And we are going from clusters of maybe 32 to 512 GPUs that most people would be deploying last year to thousands of GPUs today, because thanks to OpenAI. And the requirements for networking are very different. So again, if you put your Ethernet network as is today to do machine learning workload, it will suck.
Right.
Can we build better Ethernet? Potentially, there's a lot of efforts in the industry. Can we make InfiniBand look more like Ethernet? Possibly, yes. So feature will show, but there's much wider ecosystem of Ethernet than InfiniBand. Even so, both kind of have their SDIs or their kind of standard bodies developing both. And obviously, if you are large enough, you want to have some ability to buy from different vendors.
Right.
And this is probably where most of like unwillingness to deploy InfiniBand is coming from. Because if networking is not your competence and your workload are high value, InfiniBand is probably the default choice. However,
Right. Well,
if you are larger, if you are at size of public cloud, probably, especially given what happened in a couple of years with the supply chain, whatnot, you might think differently. So every company in the world that is building silicon, selling silicon, is thinking what's next, what to do with it, how do you potentially merge two technologies, how do you use what makes sense. And again, there are people like us talking a lot distributed networking. There are people who are still in love with open flow, saying everything has to be programmed centrally. And the truth is always somewhere in between,
some
right?
people
So
still think
if
that
we
way.
come back to it, at the end, we know that it's really the kind of half-half, where you want to centralize policy but distribute computation. This is really the working scenario. So I would think we will see some kind of coming somewhere in between. Again, I'm talking for myself, not for.
But it's,
for
I
my
mean, to me, it's really exciting. I mean, to me, I feel like, yes, I agree with everything you said. It's, and there is this, it's kind of like all of these approaches are being experimented with today, and everyone is going to make decisions based on their own requirements. But to me, it's funny that's kind of like these high level kind of trends, like, or patterns in a sense, kind of how they kind of repeat themselves, right? It's and it's going to be interesting to see how all of this progresses. On the AI side,
parallel to this discussion is really programmability part. So Intel has shut down Barefoot. It's not a secret.
Say that again.
Intel has shut down Barefoot for most parts.
Oh, okay.
So the most programmable data center chip is not there anymore. Which brings us to question, how much programmability do we need? Whether someone needed it all, or maybe you're just okay moving IP packets from left to right as fast as possible. And I think it's somewhat related to our discussion, because the promise of Barefoot was you can program everything on fly at line rate and make your application perform even better. So the question is, again, if it would have been so great, why did this happen?
Well, to me, I think it all pertains at the end to this notion of the right tool for the job and starting with a use case, right? A lot of times, we get excited with technology or capability, right? But I remember, like, to me, when it came to programmability of Ethernet silicon, like, yes, I mean, you want to have a malleable mind, because at some point there's going to be features that customers want. But then, like, every time, once you have, what capability you want, whether it's security or this protocol, etc. Obviously, you want to program that in a way that makes it the cheapest, the fastest, etc. So, like, there is no more room for programmability. So other than experimentation, it becomes hard to find what the actual use cases are. I remember, like, us kind of struggling with that when we were looking at it. But so to me, I think the maybe the lesson here is always to start with the use case, right? And try and figure out, if I'm going to start a company, if I'm going to start a project, if I want to add a capability to my product, right? Just be very crisp and clear about what it is that you are solving, right? Before,
and maybe this is where machine learning can help.
Yeah. Well, we're talking about programmable networks, but isn't that really what artificial intelligence eliminates? Is getting away from having humans. And I was looking while you guys were talking, Mansour. You said a thing this morning from another discussion you had, and something that just jumped out at me. Is a stated goal of AI, and the answer is humans are stupid, slow, and unreliable. I think that says so much. What's that?
I think I said that a bit earlier, but I think I said it a bit more diplomatically than that. But yes, that's what I had in my notes. Yes,
we're not diplomatic on this show.
There is actually, on this note, there is a there is a I'm going to quote. I think it's Warren Bennis, right? But he had this image of like a dog, a man, and a computer, right? And like you need the three to run your network, right? Like the role of the computer is to run the network, right? The role of the dog is to keep the man away from the computer, and the role of the man is to feed the dog. So
I've over the years doing presentations, and this goes all the way back to probably the turn of the century, but I have, and I'm sure all of us have our own versions of this, but I've always talked about the fact that that human error can account for, depending on what network you're looking at, anywhere from 60% to 80% of network outages. And
both Microsoft and Facebook actually published the number. It's in 40s, but it's huge, right?
Yeah, and and I would use that, and for a lot of different technologies. I think I would back, if you look around 2000, when I was talking about things like that, I was probably talking about Juno software or MPLS or things like that. But just stating that that piece, gets heads nodding in the audience. People have always looked at, I know that's my major problem, is people make mistakes and people are clumsy and people have different opinions about how things should be done. And if we have that deterministic software in our network, it eliminates a huge amount of that.
So Jeff, let me just on this exact point, right? I think that you're right, but there is more to it, and this is why I was referring to the trust a human is putting in a computer, right, to run their network reliably. And if you do automation wrong, right, even if you do determinism wrong, it can be disastrous, right? Like, so it's one thing.
Radius is now a whole network, yes.
If you take one piece of configuration and it has an error in it, and you push it to one switch, it's bad, but you can recover, right? But now take a piece of configuration that has an error in it, and then deterministically push it to 100,000 devices in one shot through your speedy automation, your powerful automation. That's how you get in the news, and that's where you lose millions and millions of dollars, right? And this is where network engineers get PTSD, right? So I think that So the trick is, how do we make these automation systems reliable? And if you look at Apstra, just to talk about Apstra for a minute, as I mentioned, we have this whole distributed data store that is collecting all the state from the network. And then we have a graph representation of all the state. Now, when I say that, actually I'm lying, because we have two of them. You have two of them. One is a staging environment, and then the other, and it's a mirror of your active environment. So we have the two of them, and they're there for a reason. If you want to make a change, you go first into the staging environment. So it's not just about automating, it's also about like the workflow for automation to really guarantee this reliability. But first you do the changes in the staging environment. There, the software will mathematically tell you, hey, are the changes, do the changes you're proposing even make sense in the context of the network that you have running? And if these changes don't make sense, then it will not even allow you to push them, right? So once you propose all the changes you want to make, then you go to a commit area where you can go and review one by one every piece of configuration that's going to get pushed in your network. You can review every cabling change, every new virtual network, every security policy that would be changed. Only when you go and review them, do you go and you press commit. And when you press commit, the first thing that happens is we take a whole snapshot of the entire environment, right? Because you want to have fail-safe, you want to have, kill switches, right? All of that. And so you take a snapshot, and then these changes get pushed into your active network. It's a pub/sub system, and so these changes get pushed in your actual network. And so from that point on, we don't stop there. We start collecting telemetry, and then we confirm through tests that we run over this telemetry that indeed the changes that you've proposed took effect, and the intent you had in mind actually took effect, right? So like the network is behaving as you expected. So at this point, everything turns green. So like we've gone through multiple, steps in the workflow, but we're not even done. At this point, you have these snapshots. You have not only this snapshot of this last change, you have snapshots across all of the changes you've done in the past. With you know exactly who did them, with what level of authority, etc. If you're unhappy, let's say the application team is not ready, you can go back and roll back the entire network level. So I describe all of this not just to pitch Apstra. Of course, we're very proud of like everything we've built, and our customers benefit from that every day. But it's really to illustrate what it takes to build reliable software, or software that you can trust, that it will reliably do the job, deterministically do the job. So it's not just about taking a configuration and pushing it to 100,000 devices. It's about having the ability, or 10,000 devices, or 20, so a large number of devices. It's about how do we get the software to do it deterministically correctly, right? So that you get this reliability that you need. And this is where I think, going back to AI, I'd say if you want the human to trust it, it needs to be deterministic. And so a pilot, if your software is the pilot of your system, it needs to be deterministic. And yes, there's going to be a role for AI for sure as the co-pilot, in case there are some issues you want to troubleshoot, or you want to address areas of your network which you don't have control over.
So this brings us to a very interesting topic, which is probably a topic for our future discussion: digital twins. How do you validate your intended state before actually deploying it, right? And I actually presented enough stuff about Microsoft. In Microsoft, we had an environment where you would define your topology, and it will go and fetch all the images from working devices, fetch the configuration, and build it as container networking for real. So with high fidelity of forwarding, so you could actually have real digital twin of your network and try to apply new changes to it. Now, what Apstra built in terms of validation of intended state, so you apply your changes to your operational state, and you see whether you meet your intended state with the changes, right? I think next step to that would actually virtually build the digital twin, run all the changes on it, hopefully with the same software you're using in production, hopefully with the same configuration you're using in production, and say, it's green, it can go, and then with push of a button, you would just go and deploy it in production and retire.
No, totally agree. And we have a close version of that, which Ryan can attest to, is Cloud Labs, right? Where at the end you can build a whole virtual environment with virtual switches, virtual versions of Juniper, Arista, Cisco, etc., and then you can try it out, right? The challenge there becomes like, is it capturing exactly my physical environment, right? But then like it can really get you very far, right, in terms of validating the design assumptions that you're making. But no, this is a very good point. In fact, that just yet one more kind of step in the workflow, right, in terms of like,
so this is proof it's in the pudding. You can model as much as you like. There's devices with their bugs and tweaks and God knows what, right? So I would say it's not directly related to ML, but it's a very important step towards high reliability to be able to actually test changes you are going to implement your network before going into production.
Well, and I think it does. Digital twin plays a lot of space, a lot of the same roles in the ML space, and even in the natural language processing or generative AI space, if we want to call it that. because I've had those conversations over the past month or so. Is, you know, if we're building out workflows that are utilizing generative AI, or building out workflows that are actually utilizing ML logic to do certain tasks, how do we validate and how do we test what the generative AI spits out? You look at responses, you can jump on ChatGPT or any of them right now, and you can ask it a question 4 different times, and it's going to answer to you 4 different ways, and it's not going to be exact. So your accuracy on your results from that type of stuff isn't going to be the same every time. And so where I circle back to that conversation is the notion of thinking about now adding a separate model into your model workflow, where you're pumping out information and a response from one specific model, and then you're doing it against a separate model like a digital twin, and validating that those two are relatively similar in response through even a third model. Or you have a second one that does the validation before it then kicks off. Because if you're using something like a vector database, semantic searching, things like that, to return results based off of ML models and things like that, 2 separate models should return very, very similar results, either from like configuration or from documentation or wherever the source is. And if they hit a certain percentile in validating the 2 together, you can call that a pass and pump it over to like a natural language processor to give you an output, or push that into your infrastructure or whatever the next step is in your pipeline. So yeah, it plays a key role there. And there's some interesting conversations that have been happening around that as well.
Love it. So this is an example of how, you know, machine learning itself is not doing it like you're adding kind of, right, like you're closing the loop in a sense, right, by providing feedback, right? So that
domain expertise is always one of the most important factors. Right. If your answers are incorrect, if your data is not correctly labeled, you know, garbage in, garbage out. Simple.
Yeah. Well, it's not just garbage in. And so maybe Ryan, we can get ChatGPT to learn that I've never worked at Cisco, right? It's every time I ask it, it tells me that I've worked at Cisco, right? So it's actually
maybe
true.
You did without knowing.
But you know, if you understand the probabilistic aspect of how it works, you understand why. I've worked at Arista, I've worked at Big Switch, at Apstra, of course, and every one of those companies, I had co-founders that, you know, may have worked at Cisco, but all of them actually competed with Cisco, and Cisco is obviously the biggest name in networking. So I imagine that, like, if you're picking up from the web, right, the corpus of data, which is the web, then every time my name is mentioned, probably like there are many, many more mentions of Cisco than any of the companies that I actually worked at. And so this is why it actually thinks that I worked at Cisco. This, to me, this is a good illustration of how, you know, probabilistic predictability can be convincing, articulate, yet dead wrong, right? So maybe we'll fix that at some point.
Yes, and that's like amazing continuation of this discussion on another episode.
Yeah, I was going to say we're a little bit over the top of the hour, and this is a great discussion. So I think, and this is the way it happens with a lot of our shows. We get some really great guests on there, and we go, you know, we kind of go down the rabbit hole and realize, oh, we've used up our whole hour here, and there's still a whole lot to talk about. And this is definitely a case of that. I think if you guys are open to it, we'll invite both of you back to continue this discussion because this has been a lot of fun. I love shows where I'm learning stuff too, and I definitely learned in this show. But Mansour and Ryan, I want to thank you very much for joining us here. And I kind of feel like I'm sort of cutting off a really good discussion, but I guess we've got to stop somewhere. But I hope you can join us on a subsequent show.
Absolutely, let's keep doing it. I appreciate it.
Thanks everyone for attending. Thanks everyone.
Thank you, Jeff and Jeff.
For being with us. Right. Jeff, Mansour, Ryan.
Thanks everybody.
You guys.
Bye.
Thank you. Bye bye.